Hi everyone. Today we'll resolve the paradox posed by the so-called anomalous Zeeman effect in atomic spectroscopy by looking at the consequences of having both orbital and spin angular momentum at play in the atomic electron Hamiltonian. But first I want to tell you a little bit more about spin and its interaction with magnetic fields. First, let's review the elements of our theory of electron spin. The spin vector components are represented as operators by the 2x2 Pauli matrices. In direct analogy to orbital angular momentum, the square of the total spin is h bar squared times the half-integer spin quantum number, little s, times s plus 1. Eigenvalues of the individual components are simply the spin magnetic quantum number m sub s times the quantum of action h bar. In a magnetic field along Z, we have a trivial 2x2 Hamiltonian whose eigenvalues are given by the diagonal elements, with corresponding eigenvectors which are purely one spin component or the other. We see that the first moves up in energy, which we expect from a magnetic moment pointed antiparallel to the magnetic field. Because the spin angular momentum and its magnetic moment are antiparallel, however, this corresponds to spin parallel to the field, and so we call it spin up. The other moves down in energy, consistent with a magnetic moment parallel to the field, which has angular momentum opposite to the field. It can be called spin down. Note that we can compactly represent the eigenenergies by this simple function of the spin magnetic quantum number m sub s. We can use the stationary states of the simple spin Hamiltonian to calculate the state evolution of a spin in a magnetic field in which it is not an eigenstate. For example, let's say we prepare a spin as an eigenstate of Sx, for example by placing it in a magnetic field along x and waiting for slow relaxation processes that we ignored in our Hamiltonian to take the system to its lowest energy state. For a magnetic field along the negative x direction, that's the state with a positive eigenvalue of Sx, the ket labeled plus. Now let's suddenly rotate the magnetic field along z. The state is not an eigenstate of the new Hamiltonian, but we can decompose it into a superposition of eigenstates that diagonalize the Hamiltonian, and which each evolve in time with a different complex exponential given by its energy. We can now use this to determine how the expectation value of spin along x changes with time. We simply sandwich the operator by the state, remembering to not only transpose, but also complex conjugate the bra on the left, converting it from a column vector to a row vector. The result is a quantity which oscillates in time. But how is spin conserved then? If Sx is changing, where does the spin go? By calculating the expectation value of spin along the y direction, Sy, we see that it too is oscillating in time, 90 degrees out of phase with spin along x. This is simply the quantum mechanical version of a process we're all familiar with: the Larmor precession of an object with angular momentum subject to a torque, such as a gyroscope. In this classical example, it's a mechanical torque due to gravity, whereas the spin undergoes precession due to a magnetic torque caused by a magnetic moment in a magnetic field. Note that the precession frequency is controlled by the Zeeman splitting from magnetic field magnitude. This field control over spin precession Larmor frequency is precisely how we can spatially image using magnetic resonance imaging. Powerful electromagnets are used to create strong magnetic fields and field gradients, so that only a small volume will have the Zeeman splitting that corresponds to a resonant excitation from narrow band radio frequency electromagnetic waves. This selective excitation is then sensed by inductive detectors, pickup coils. By scanning the resonant slice around its space, by changing the electromagnetic coil currents, images of deeply buried structures are created. MRI works by acting on the spin of the nuclei, not electrons, which is enabled by the much smaller nuclear magneton due to much larger mass of the nuclei, and correspondingly small Zeeman energies and radio frequencies for excitation. Although impractical for imaging human biology, electron spin resonance at around 28 GHz per Tesla for the free electron is, however, very useful for study of inanimate samples such as organic molecules and solid-state materials. Now we can get back to the issue of anomalous Zeeman effect of atomic spectra in a magnetic field. Both the orbital and spin angular momenta of the electron have magnetic moments which couple to the magnetic field. But as we saw, the relativistic nature of the spin makes inclusion of a non-unity Thomas G-factor necessary. We can of course diagonalize the Hamiltonian and determine the Zeeman splitting for each term separately, but how do we go about diagonalizing this expression with vectors L and S that are in general not parallel? The key is to notice that the total angular momentum, L plus S, is conserved. We expect that the energetic splitting will be on the same form as before, but with an effective G factor. Let's see how this works out. First, we project both vectors onto the conserved angular momentum axis by taking the inner product with a unit vector along J, L plus S. For a magnetic field along Z, this then picks out the Z component of J, which has eigenvalues h bar times the total magnetic quantum number m sub j. Carrying out the dot product yields an expression that is mostly known quantities in terms of the individual quantum numbers. But what's the dot product between the spin and orbital angular momentum? This can be seen by once again looking at the conserved quantity J squared. Substituting this quantity into our Hamiltonian entirely converts it into a scalar energy quantity, which is proportional to the magneton times the magnetic field times the magnetic quantum number m sub j, with a coefficient out front that depends on little l, s, and j. This is the so-called Landé G factor. Here's a few useful examples. When the orbital quantum number is 0, we just have the magnetic field interacting with the spin, which we know has a G factor of 2. Landé correctly predicts this. For L equals 1, the total angular momentum J can be 1 plus 1/2, 3/2, or minus 1/2, yielding 1/2. In the first case, the Landé G factor is 4/3, and in the second, 2/3. So from the 6 L equals 1 states, that's 3 orbital projections times 2 spin projections, 4 of the J equal to 3/2 states, where m sub j is minus 3/2 minus 1/2, plus 1/2 and plus 3/2, have one G factor, and the 2 remaining J equals 1/2 states, with m sub j equal to plus and minus 1/2, have another G factor of half its value. In a magnetic field, the 6 split like this. Now let's look at transitions to the L equals 0 derived states. The selection rules with Landé spin-orbit coupling are analogous to the orbital selection rules. Changes in quantum number J are plus or minus 1, and changes in the total magnetic quantum number m sub j are 0 and plus 1 or minus 1. This means that only the 4 J equal 3/2 states can radiatively transition to the J equals 1/2 states, and only the m sub j equal to plus or minus 1/2 states can transition to both L equals 0 states. This leaves 6 distinct transitions. The energy of the spectroscopic shifts that we observe by dispersing the emitted photons through the spectrometer are proportional to the difference in the products of Landé G factor times the total magnetic quantum number m sub j for initial and final states. We can now see how multiplets more than the Lorentz triplet are created. In this example, the spectroscopic line splits into 6 in a magnetic field, each separated by 2/3 of the Lorentz splitting, and all lines shift with magnetic field. It is this spin-orbit coupling that explains the anomalous Zeeman effect.